Okay, welcome to sixth lecture on stability of structure. So, you are considering Augustus column, this column a system, this is called Augustus to demonstrate the influence of modal interaction. We will demonstrate that how two apparently imperfection insensitive mode become imperfection sensitive due to modal interaction. Okay, and this is demonstrated using a simple example. This is a column, okay, and rigid column which is hinge here, and it is restrained by two springs C1 C2. These are both are rotational spring, right? And then we have as discussed in the previous class. So, we projected in x, z and y, z plane, and then we satisfied the equation for the direction cosine to find out the cosine of phi. Phi is the angle with the z axis, okay, the column, right, and then we basically wrote down the potential energy functional, okay. Theta 1 and theta 2 are the 2 degree of freedom. Please note that there will be two independent coordinate. So, this is 2 degree of freedom coordinate, okay. So, theta 1 theta 2, because phi can be expressed in terms of theta 1 theta 2 by virtue of this direction cosine law, right. So, then we basically need to simplify this expression, and then we have considered sin theta, the expansion of sin theta and cos theta, sin theta 1 and sin theta 2, okay. We included both theta as well as theta and theta cube by 3 term, factorial 3 term, and then while squaring we retain only theta 1 square, theta 2 square, and then theta 1 theta 2 this cross term, okay. The sixth order terms are neglected, okay. Then for the equilibrium path we have minimized the potential energy functional, and then we obtain this equation. Please note that if we want to do a linearized analysis, then what will happen? We are going to retain only this thing and this thing, right, and all this because theta 1 cube, theta 1 theta 2 square, theta 1 square, theta 2, these are coupling term, okay. And then imperfections only linear, we are assuming that imperfection alpha 1 and alpha 2 are same. Imperfections were given as initial rotation to these springs, okay. C1 is rotational stiffness C1 C2. So, now from here we know that if we for linear analysis, from linear analysis, so linear analysis linear analysis we can find out if we do this solve the eigenvalue problem, then there will be two critical load and then this one is C1 by L and another one P critical 2 will be C2 by L, okay. L is the length of the the bar, L is the length of the bar. Now, I will then simplify and I will write the final expression, okay. And in that case when C1 is equal to C2, then the expression will be, then all these things will be simplified and then we will retain still some nonlinear term, and what you will get I will write down the expression. Then of course, then PCR1 and PCR2 critical load will be nothing but both will be C by L, okay. That is the critical load, and for that case and theta 2 is I have written plus minus theta 1. Let us consider theta is equal to theta 1 is equal to theta, okay. So, I am assuming theta is equal to theta 1 is equal to theta, okay. If you assume theta 2 is equal to minus theta 1, that is also fine, okay. Then if you substitute, then we will get the expression of potential energy expression will be C upon L C theta square, sorry, C theta square minus PL theta square plus theta 4 upon 6 minus 2 C alpha theta, okay. This will be the expression for the potential energy when this mode multiplicity is occurring, okay. I am substituting theta is equal to theta 2 is equal to theta 1 is equal to theta, and both the critical loads are identical, okay, multiplicity of, then this is the expression for phi, okay. And from there you will see that if you differentiate del pi by del theta is equal to 0 for equilibrium path, here you will get P theta plus theta cube upon 3 is equal to PCR theta minus alpha, okay, and del 2 pi del theta to 0, from where you will get PCR. This will give you, theta square is equal to PCR by P minus, and you can see the whether these expressions are correct. Okay. So, from these two you see that. Okay. Now, what we are going to do for modal interactions, what we have done in the just to show the imperfection sensitivity. So, we will just substitute, you see that PCR by P. So, we can write PCR is nothing but 1, 1 P into 1 plus theta square. So, combining these two expressions, from these two, let us relate, let us relate theta with alpha, okay, with alpha. So, how you will relate it, you please see that theta cube minus alpha theta square is equal to theta cube upon 3, okay, and from here you will get alpha is equal to 2/3 theta cube, and then I will just write P by PCR. So, then P by PCR will be nothing but 1 divided by 1 plus theta square, which is nothing but 1 minus theta square, and then 1 minus to some constant whatever. Okay. So, 2/3 theta cube 1 to the 2 by 3. Okay. So, odd 1 theta square 1 minus theta square. So, theta square will be 1 minus divided will be 3 alpha upon 2 3 alpha by 2 and 2/3. Okay. So, I will just remove all these things, or from here I can write P by PCR is nothing but 1 minus some constant, okay, maybe some constant alpha, some constant C cube, maybe I can write C cube alpha to the power 2 by 3. Okay. So, what we see, this follows 2/3 imperfection, alpha is imperfection, 2/3 power law. Now, what we, so if this is for what? For combined system, for interacting system, right? For interacting system. Why it is interacting? Max, because PCR, what is equal to PCR2 is equal to C by L, right? And we have considered the coupling term between the two mode, right? We have considered nonlinear term, that's where this cubic and all other terms are coming, right? But now, go back to the individual. So, if this bar, I am assuming that C2 is very, very less than C1, then what will be the buckling load? C by L for single degree of freedom system, for a rigid bar restrained by a rotational spring. What was the critical load? C by L. We have done in the first, where it shows the symmetric stable bifurcation, right? And so for a SD of system with C1 basically very, very less than C2. What was the P by PCR was what? For that is symmetric stable bifurcation, the system which was showing the symmetric stable bifurcation, right? The first example we have considered a rigid bar restrained by rotational spring, that was showing the symmetric bifurcation and stable post critical path, right? For that it was not imperfection sensitive, it was what? P by PCR, it was 1 plus some constant alpha to the power 2 by 3, it was plus, theoretically it was plus. That means critical load, load carrying capacity increases with imperfection, right? load carrying capacity increases with imperfection, but here because of interaction what is happening, this plus become minus. So, it become imperfection sensitive, you see that. So, independent modes which were apparently imperfection insensitive become imperfection sensitive due to, and what is the reason for that? Modal interaction. Okay. So, modal interaction triggered imperfection sensitivity, that is the takeaway from this. And how it is demonstrated? We have considered the Augustus column, which is 2 degree of freedom system restrained by 2 rotational spring, right. So, you see the importance of modal interactions. So, apparently imperfection insensitive system become imperfection sensitive, but its imperfection sensitivity 2/3 sensitivity. 2/3 means what? Mild imperfection sensitivity, right? Mild imperfection sensitivity, imperfection sensitivity, mild, right? Now, so this is the takeaway from the modal interaction. So, we can write down, please write it down, that modal interactions may trigger imperfection sensitivity in a system. So, we will write modal interaction, but how will I ensure modal interaction? Look, if you do linearized analysis if you do, that means eigenvalue which lead to eigenbuckling problem, you will get uncoupled mode only, because you do, right. But they are actually coupled. If you consider geometric nonlinearity, higher order nonlinearity, they are actually coupled. So, these buckling apparently separated buckling modes are actually coupled, and then when you do a linearized analysis, that lead to eigenbuckling analysis, what for cell kind of structure we will see there are multiplicity of mode, and modes are very close. That means they tend to interact because they are coupled by geometric nonlinearity. Okay, and that is the reason basically what happens in cell buckling, why the critical load drop, because all this mode multiplicity or closely spaced mode they interact, and then some of the modes were imperfection sensitive, some of the modes are imperfection insensitive, but most of the modes be whether it is stable by symmetric mode or of course asymmetric mode will be more imperfection sensitive, right, comparing symmetric mode, right. Even symmetric mode will also be imperfection sensitive, mild imperfection sensitive. Asymmetric will be more imperfection sensitive following half power. So, when they will give rise, when they will interact, it will further enhances the imperfection sensitivity, right. So, that is what basically happened during cell buckling, and that caused huge reduction in the critical load. So, modal interactions trigger imperfection sensitivity, in modes which were otherwise imperfection insensitive. Clear? That is a big thing, and how we have demonstrated. So, I will give you an example for that. Okay, you must have learned in your steel design class. The button column, right? Button column, example of button column, right? This columns, they are connected, or reticulated column, by this button system, right? Either they are welded or riveted, right? I mean they are welded or bolted, right? This is button plate, right? So, these are the two different maybe angle channel section which are connect, and then why they are button, because you want to use them as a single unit, right. So, when it is subjected to buckling load, what kind of mode will be there? There will be multiple mode, right, but I will in. So, you want global mode, one local mode. What will be the global mode? Global mode will be this column may buckle like by out of plane bending, right. You see that this is the buckling mode, right, something like this, right. So, this is the central line, so under axial force, axial compression. So, this is a global buckling, right, buckling. there can be a local buckling. How? This is a global buckling, right? This is global mode, global buckling mode, global buckling mode. There can be another local mode. How it will be? Because they are buttoned, so there can be, something like this. This is local mode, this is local, and this is symmetric mode, local buckling mode. Why it is local? Because the portion of the column which are in between the two button plate are liable are buckling, right? You see, these are being a point of counterflexure, all these point, right? You see, this is buckling. So individually the intermediate, portion of the column between two button, because button provides some kind of lateral restraint, right? So these are all local mode, right? Now this is local symmetric mode. There can be local asymmetric mode. So local asymmetric mode, how it will look like? You see, if you want to put local asymmetric mode, will look like maybe something like this, maybe something like this, and then something like this, like this. You see that? This is local mode. Once again, local asymmetric mode, buckling mode, right? This is asymmetric, this is symmetric, right? Now, what happened for the local global mode? There can be some critical load, peak critical 1. Now, for this, see, ultimately, be it local or global mode, the buckling is happening. The buckling is contributed by the axial compression, right? So these two fellow is also when it is buckling, this will also have share of some P critical, right? I am assuming this critical load is also P here 2. Here also the P critical load P here 3. You understand what I am trying to say, right? Now it may so happen that all these modes may interact. How will they interact? Because when there is a little out of plane deformation, there will be significant onset of the geometric nonlinearity. Because of geometric nonlinearity, there will be coupling between these modes. So coupling among these modes, coupling among the global and local mode, the global and local mode, local mode can be symmetric, asymmetric, right? Modes. And because of this coupling, ultimately how it will look. So this combined mode will look like something like this. Combined mode will look, let me show it to you. Somehow you see. So this is a combined mode, this is a combined mode, combined mode. And how this combined mode is occurring? This combined mode is a combination of this global mode and this symmetric mode, right? Because this is symmetric. Similarly, there can be combined mode, global mode plus antisymmetric mode. So when this thing happens, you will see the P critical, CF, this P critical will be less than whatever the combined mode P critical, this P critical, it will be less than P critical 1 and P critical 2, okay. And then it will be imperfection sensitive. So this analysis can be done. I mean, analytically it will be maybe little challenging, but if you do even using any finite element, nowadays there are many commercial software, okay, you can clearly do this exercise in ANSYS, Abacus or whatever, any code, and you can clearly see that how does it affect, okay, the modal because of the modal. So this is one example, one instance of modal interactions, okay. Okay. Now I will solve an example. I will solve an example, that example shows the, manifest, coupled, bifurcation and snap through. Bifurcation and snap through, meaning it will both show snap through as well as bifurcation. So it's a combined things, okay. So the system, this is called Bergan truss, okay. Bergan truss, like von Mises truss, it is the combination of C, the how it looks, it is something like this. Okay. I don't know. So there is a spring, okay, because spring stiffness or axial stiffness, whatever. But so this is nothing but what? This is called what? Mises Truss, right? So this axial load is there, P, okay. This is the axial load, but in addition to that, there is another spring that is attached here, okay, and this spring is supported here. So it's a combination of von Mises Truss restrained by another spring, additional spring, okay. And I am just in giving you the dimension, and this is basically this, maybe this is L, this is L, and this height is H, height is H, okay, like that, okay. So now you tell me this truss is called Bergman truss, and it will show coupled bifurcation synaptic behavior, and let us analyze that, okay. So how will you analyze it? See, when you have to consider deformed, right, configuration, right. So you see that this point can move, this is the, I am assuming that this is spring A, this is spring B, this is spring C, okay. So now this spring, this fellow can move vertically, and this fellow can move horizontally. The point under the load P can move vertically as well as horizontally, right. So I am assuming that, when it is moving horizontally, it will come to this position, right, and then when it is moving horizontally, it will come somewhere here. So I am just drawing it something like this, something like this, okay, here, I mean, maybe not really like that, it will top of that, so I will just put it here, I will just give it there, so this is coming horizontally. So you see, what is it, and this fellow is basically, whatever it is coming down, it is coming down somewhere here, okay. Okay. So you see that. So this fellow is, this is the, so this is the vertical component, this one, this to this, okay. This is the vertical component. I mean, I may want to write this component to be V, okay, and the horizontal, this horizontal one, I mean this, I mean I read it, write it to be small h, okay. All of you got it, what. So the ultimate configuration of these become, so this, and this, you see, so okay. So now if I, maybe I am assuming this is maybe this is x, okay, I will just, so I am just, this I will add z, this is x, and this is y, okay. So if I show you this view, xz plane, how it look like. Xz plane means which plane? Xz plane means the vertical plane, right? Vertical plane, how it will look like. Now I am just, so what is happening? This is nothing but vertical plane, huh? Note that, huh? So P is moving here, and then this vertical movement, this component is nothing but V. Okay. So now, so if this V, then this distance is how much? H minus b, capital H minus b, because this distance was h, right? H minus b, right? Are you visualizing the system correctly? Okay, because then what we have to see, we have to find out this ultimately this length, okay, and please note that it will have, how we will do, this will be nothing but this square plus this square, okay, this length square plus this length square will be, so A is coming to A dot and B is coming to B dot, please know that, okay. So this length is nothing but square of this plus square of this, okay, xz plane, and then I will write yz plane, which is basically horizontal plane, horizontal plane, and here the way it, so it is coming to this position, it is coming to this position, and this was basically nothing but h, small h, and this is L, this is L. So you see that this length, this projected this length is nothing but root L square plus h square, right? So L square plus h square is nothing but this length. So this length, you see this length is nothing but L square plus h square, because this is h and this was what? This was L, right? Okay. So this length is nothing, this length is same as this length, right? L square plus h square, okay? This length, and this is nothing but, this one is nothing but h minus b, right? This one is h minus b. So this is h minus b and this is root L square plus h square, clear? This is capital H minus b and this fellow is nothing but root L square plus h square, clear? Now, so one, all of you have this too, so the final length, so initial length of the spring, initial length of springs, springs, or this spring stiffness is given by this axial stiffness of the truss. I am assuming that maybe some stiffness. Spring A and B, they are identical, okay, is nothing but root L square plus h square, right? Why L square plus h square? Because this length was L and this length was L and this length is h. So this length was root L square plus h square, right? And final length of A and B spring, A and B, this spring is nothing but root what? It will be root L square plus h square plus capital H minus small v square. Small v is the vertical deflection and small h is the horizontal deflection, right? You can please note that v vertical deflection, deflection under P, and H is the horizontal deflection, deflection, displacement, right? All of you understood. So the inclined spring, this B and A, the initial length was this, final length was this, right? So you understand the deformation kinetics, right? Understand the deformation kinetics? What about this spring? This spring is only going through extension. Extension is nothing but the horizontal H, right? Okay. This fellow was in one plane, but this is in other plane, right? This is away from the plane. You understand, na? So this is the von Mises truss. This is the Mises truss, and this point is rested by another spring. So it is like this, and it is rested by another spring out of plane in the out of plane direction. Clear? So I am just removing these two. Okay. So now this once you understand this deformed thing, then other things becomes very simple. Okay. So now we will write down the potential energy. So delta A or B, whatever, delta A is equal to delta B, whatever. The spring delta A is equal to delta B will be nothing but root L square plus h square plus h minus v square, minus root L square plus h square. This is the final deformation, this is the initial length and this is the final length, okay. So, this is the extension of the spring, extension of the spring AB, of the springs, springs A and B, okay. And so, then an extension of spring C, extension of spring C, extension of spring C is nothing but what? It's same as the horizontal, H, only H, right, because it is deforming only out of plane deformation, that is nothing but H, right, this one H, right. So, this fellow is moving H, fine. So, now we are going to write the potential energy function. So, potential energy is strain energy minus work done. So, strain energy is contributed by both the spring. So, 2 into half C1, this delta A or delta B square, okay, plus half C2, is the spring stiffness, delta 2 is the delta basically C, delta C square, okay. Please note that delta A, delta B same, okay, minus what is the work done by P? P is the vertical load. So, only component it will work on is the due to vertical level. So, P into V, right, minus P into V. So, strain energy minus work done, strain energy in spring A, B, that is why multiplied by 2 because both the spring are working, right. So, now I am just substituting, we will simplify, just substitute delta, delta B and delta C expression over here. So, C1 and this one will be nothing but L square plus H square right, this one. Now, may I remove this plot, right. This is Bergan truss, okay. It is a combination of von Mises truss and a spring. The spring is restraining the point, that apex, the top point of the head of the von Mises truss, okay. So, pi. So, once we find out this, then for equilibrium we have to find out equilibrium, right. So, equilibrium configuration, for equilibrium we have to do delta phi is equal to 0, and because this is 2 degree of freedom system, we have horizontal translation and vertical deflection, right. So, both. So, delta phi by what? Delta phi by delta V into dV plus del pi del H into dH must be equal to 0. Now, dH, dV and dH cannot be 0. So, from here you see that del pi dV is 0 of course, and then del pi del H is 0, right. So, that is what. So, this will give you two equations. So, let us writing down these two equations. So, del pi del V will give you minus P minus 2 C1 H minus V root L square plus H square plus H minus removing this. This must be equal to 0, and for the other one basically you will get C2H plus 2C1H root L square plus H. equal to 0. So, now we will see. So, of course, you can take H outside, So, from here, so this I am writing equation 1 and this I am writing equation 2. Okay. So, two equations we got. Now, let us first write equation 1 and 2. So, these two will give two equations, but we have to simplify. Look, from 2 you see that from 2 H is there in both the expression, here is H, here is H, right. From 2 either H is 0 or the rest of the expression is 0, right, or the rest is 0, the other is 0, okay, or the other one is nothing but 2 2 C1 2 C1 H 2 C1 2 C1 or root L square plus H square plus H minus P square minus root L square plus H square and divided by root L square plus H square plus H minus P square is equal to 0. Look, when H is equal to 0, that means it cannot happen. So, that is nothing but fundamental path, right. H is equal to 0 means what? This was the non-trivial, that is the fundamental path, right. It was not even, that means there is no deflection configuration, right. So, this one is the primary path, H is equal to the primary equilibrium path, right. This is the primary equilibrium path, primary equilibrium path. Primary equilibrium path is given by H is equal to 0, and the other one, this gives us the secondary equilibrium path, right? Secondary equilibrium path. Now, please note that there is equation 1, okay. We are yet to do something on equation 1, okay. We will do, no problem. So, what we are going to do now, so from equation 2, we are obtaining primary equilibrium path for H is equal to 0 or the secondary equilibrium path. So, the other expression is 0, and then please note that we never forgot the first equation, okay. So, now what we are going to do, that we substitute H is equal to 0, that means the primary path. H is equal to 0 means primary path, primary path in 1. We are going to substitute H is equal to 0 in this equation, in equation 1. So, then you will see that this will give you, and simplifying we get P is equal to 2 C1 V minus H root L square plus H minus V minus root L square plus H square and divided by root L square plus H minus V square is equal to 0, okay. Sorry, this is equal to 0, so P is equal to this. So, P is equal to, so in this expression you are going to get an expression for P, right. So, H is equal to 0, you are substituting, then in terms of P you are getting, okay. So, this is what? This one is what? It is the primary equilibrium path, right. So, primary path that I have written, right, okay. So, let us plot, so this, we can plot it, okay. So, if you plot it, how it will look like? Plotting this one, plotting. If you plot it, it will look like this. This is P, so you can clearly see that for 0 is equal to 0, so here is basically V, okay. So, if we put V is equal to 0, then it will be 0 and then there will be this situation, like, and then like something like this and then this, okay. So, this point is nothing but for H, and this one is nothing but 2H, 2H. So, in 3 places it will 0. Please check whether it is correct. Okay. Oh, H is equal to, V, if V is equal to H, then yeah, this will cancel out and things. Okay. So, you see that we get something, something like this. Okay. This is the primary equilibrium path. Okay. Primary path. I am just writing primary path. Primary path. Now, for the secondary equilibrium path, for secondary, which one is this one? For secondary path, for secondary path, secondary path is this one, this equation, right? We have to simplify it little bit. So, if H naught is equal to 0, of course, here. Okay. So, here if you see, then I think I just missed it, C2 plus, there were some C2, okay, C2 plus, please, I just inadvertently erased that. Okay. So, secondary equilibrium path, I'm just, from here I am simplifying it. Okay. Please note that. So, it is, please note that this is equal to minus C2. It involves little manipulation, but do not worry, this I will going to get equation 3. I will soon complete it. L square plus H square plus H minus V square minus root L square plus H square, and then root L square plus H square plus capital H minus small v square. Okay, this was simplified. Now, we will combine equation 3 with 1. Okay, equation 3 we will combine with 1. Okay, this expression. So, then if you combine with this, then what will happen? Of course, this expression will simply, so combining 1 and 3, combining 1 and 3, that means secondary 1 and 3, secondary and primary path both are, we are substituting equation 3 in this. Okay. So, then you will see what you are going to get, it will be P minus E minus 2 C1 H minus small v minus C2 by 2 C1 is equal to 0. Okay. You please check it, but I hope that we are doing correct. Okay. So, from here you will get P is equal to C2 into capital H minus V. You see that? So, you plot, now we are going to plot this one. So, this if we plot, how it look like? P is equal to this, and here it is P, P, and then here it is, V, V, here it is, this is like this, it will go. So, it is C2 capital H, and then here it is basically H. Okay. This is 0, 0. Okay. Now, of course, so this, it is a combined system. Now, I will add these two. Okay. So, you have noted this thing, right? So, now I will combine, I am removing this part and I am going to combine these two. So, if I combine one, combining, because it is the same two path we are obtaining from two solutions, right? So, we must, the system will have this combined behavior, so if you combine, how it will look like? It will look like, well, I will just okay, and then from here C2 into H, from C2 into H means from here I am going to do this one, So, this is stable, stable. Look what is going to happen. You see, both. So, if the system I am loading by displacement, I am going like this. Okay. If I go by load, here, from here you see that this path is bifurcating into two. One is following the, we are following and reaching a limit point, while it, because this is the maximum load and that point where it is attaining maximum load. So, until this it is stable, right, then it become unstable, right. Why it is stable? This positive slope, because here, all this dv is greater than 0 for stable, right. See, I did not explicitly obtain the stability, because I do not want to unnecessarily complicate the equation, right. But you can understand that this is a stable path, because it is a positive slope. But when it is reaching here, either it will follow this path or it will follow this path. So, if it follow this path, then it will go, and then if you make it displacement control, it will suddenly jump into this by snap through. But if you do load control, then it will follow this path. Clear? Similarly, during unloading also. Now, if you go this, and then instead of this, if it follow this path, then what will happen? From here, if you go by load control, it will suddenly go into this position, right? Do you see that? So, this implied bifurcation, and even in bifurcation also, it will suddenly, from here to here, it will, not suddenly jump, because from here to here it will not be, snap through of things, because it is, it's a adjacent path, okay, but it is unstable path, because the slope is being negative, right. This path is unstable. This path is unstable. Why? Because dv is less than 0, the slope, right. But if it try to follow this path, at least there will be no snap through. Snap through will only occur if you reach the limit point and you go. Do you understand that, what I am trying to? So, depending on your choice, that after bifurcation which path to be followed, right. Of course, it will not follow that path, because which one will be energetically, see, this is stable path, this is still stable path, and this is unstable path, right, right. So, unless and until you constrain it, it will not, follow a particular path, okay. Whether this is stable, this is unstable, okay. So, if you reach limit point, it will suddenly jump and snap through a locker. If you go here, then from this point, it will go there, okay. So, it shows coupled bifurcation as well as snap through, right. Somehow you have to, you have to restrain the, system in to achieve this, so that it does not follow this path, okay. Okay, because otherwise it will come there and it will, if you follow this path, it will it will, gradually follow these things, okay. But it is an unstable path, okay. Please note that. Okay, so what we have learned? We have learned a system which shows coupled bifurcation as well as snap through behavior, right? And you know what is snap through, which one is bifurcation, right? So it is not that whatever 4 fundamental system we have discussed, there can be system, mechanical system which will show coupled behavior. So, for example, this is a simple system of Bergman truss, okay, but if you consider like for in cell buckling, what happened is that you have bifurcation, but snap through also occurs, okay, because in cell buckling, so this once again this coupling of this snap through as well as bifurcation, okay, occurs in cell buckling, okay, when the cylindrical cell under axial force and when a spherical cell under uniform pressure buckling occurs, okay. So, we are going to start, one more thing I would like to point out here. You may recall when we are talking about the asymmetric bifurcation, okay. You may recall that that part was something like this, right, okay, and then this was the asymmetric bifurcation, and if you can recall, how the path was this for the perfect system, these were for the imperfect system, right, something like this, isn't it, right? So, this was alpha greater than 0, and here it was something like this, right, and these are the point, so this was the stability boundary, if you can recall, right, isn't it? Please, here also this quadrant was also alpha greater than 0, right? So, here I just show the imperfection sensitivity for this, right. So, P by P here was 1 minus alpha half, right, alpha half, okay. So, alpha half means what? If you take square root, then plus minus, okay, and then if you can recall, then the way I have drawn it was something like this, right, isn't it? So, I was showing to you that this part, these are unstable path, these are these are unstable and these are stable, right, because it is rising, it is decreasing path, right, ascending, descending, and this was ascending, right. So, for any alpha, for any specific alpha, this is imperfection sensitivity diagram. So, here I was just talking about P by P here, and this was the basically root alpha, right, and it was something like this. So, what will happen? You see, let me, this 2 root, how this 2 root corresponds to, you see that here if you drop, here if you drop, here if you drop here, and then same thing here you drop, So, you see what will happen, you see. So, then so this, so for any alpha there will be 2 roots, okay, this is one root, this is one root. So, this root corresponds to this, another root corresponds to this, okay, one is stable, another is unstable, clear. So, for this, for this it is unstable bifurcation, that is why load, it is being imperfection sensitive, load is decreasing. For the other one, it is load is increasing. You understand that? Similarly, for this one, so plus minus alpha for 1 in this branch, load is decreasing, because see this point are the limit point. So, from limit point is diminishing, the path is going down, that become imperfection sensitive load is. But if you go to this the top, the load will increase, because it is imperfection insensitive. So, that is why it is an upper limb. Similarly here. So, what I just wanted to show you this correspondence actually, okay, the correspondence between the stability diagram and the imperfection sensitivity diagram in case of asymmetric bifurcation with stable unstable behavior, okay. Please note that, thank you. I mean removing it, okay, good. So, now I think basic system, toy systems we have covered. So, we have learned the just to summarize that we have tried to formalize the stability problem in terms of energy formalism, okay. The minimization of energy gives us the we have seen that minimization of energy gives us the equilibrium configuration that we knew from the previous courses. But then in order to find out the nature of the equilibrium, whether it is stable, unstable or neutral, you have to explore the higher order derivative, okay, the Hessian of the potential energy functional, and then depending on the single degree or multi degree freedom system, right, it will give you to a multi degree freedom system will give you a eigenvalue problem, linear, so you can linearize all the problem, okay. Sometimes linearization will be meaningful, sometimes it will not be meaningful. For example, if there is a significant pre-Bernoulli nonlinearity and there is huge snap through kind of behavior, okay, then the linearization will be meaningless, right. However, if you you can ascertain on the stability behavior looking at the functional expression of the potential energy function. So, which shows the system which shows the symmetric bifurcation with stable or unstable post critical behavior are marked by the quadratic term, quartic term and sixth and eighth order term, whereas the system with asymmetric bifurcation and with stable unstable imperfection, stable unstable post critical behavior is marked by the odd term in the expression such as first order term, cube term, fifth order term and seventh order term. Those are notoriously imperfection sensitive, and there are other system which does not show bifurcation, but it shows snap through. So, they are the stable unstable transition occurs dynamically, although we are capturing that using static analysis, but actually it happens dynamically, okay, through snap through release of kinetic energy, okay, as a heat by dissipating as a heat and things like that, okay. And then we have also demonstrated a system which shows combined behavior, a snap through as well as bifurcation has combined. There are many systems which shows this kind of behavior, coupled behavior, okay, fine. And then we have shown to you that modal interaction, the implication of modal interactions, apparently imperfection insensitive mode become coupled and they become imperfection sensitive, okay. So, this basically ends our discussion for the first two chapters, okay. So, now we will start to look into little real example, okay. So, the first of everything we will start with the beam column, okay. What actually happens, and how the governing we have all learned in our undergraduate or sophomore level classes that how the equation for the beam bending, right. We will see that if there is a column, the beam is under compression, axial compression, then it is called beam column, right. We will see how what will be its governing equation and how we will differ, right. So, this is a very simple system. The way we will start is there are different approach, but we will start with a mathematically elegant approach and where energy approach, one second, from energy, okay. Why we are following energy? Because it is very intuitive and it is very easy to work with energy, okay. And you have a quite deal of discussion on energy functional in your finite element course, right. So, now when we are studying beam column, so beam column is what? A beam which is subjected to, so a beam is subjected to transverse load, moment, concentrated load, and then at the same time when it is subject to axial force P, okay, then it is called beam column, right. So, there can be some support condition, it can be simply supported, it can be cantilever and things. So, similarly you can have a cantilever, and then in this cantilever is subjected to maybe some concentrated load, some moment, and it is also subjected to axial compression. So, compression is the one which causes instability, right. Most common instability is the buckling, right. So, we are going to derive the equation, okay. So, now, so potential energy functional phi, once again I am going to consider a beam column. So, I will potential energy minus work done. So, if there is a beam column, I am not considering the loading on the beam, but because the destabilizing force is only P, okay. And then I am considering that of course, the first lesson on any stability analysis, we have to consider its equilibrium in the deformed configuration, perturbed configuration. So, I am assuming that this is maybe this x, this is x longitudinal axis and this is wx, w is the out of plane deflection, right, or I am just changing the axis, okay. This is a beam column, okay. Now, what is the strain energy? Strain energy is what? How it resists load when it is going through out of plane bending. Bending strain energy is expressed. Let us express everything in terms of W. We can express in terms of bending moment. So, you have learned that EI by 2 integration 0 to L, you know that how d2w dx2 square, right. How this is coming? Because strain energy of bending is nothing but what? Moment into curvature, right. So, moment is moment multiplied by the curvature. Curvature is nothing but d2w dx2 up, neglect higher order curvature, right. So, then moment is d2w dx2. So, it is EI. So, it is being square and half is coming, you know that, right. Why half is coming, right, strain energy, because half integration sigma transpose epsilon, right, and right. Now, what is work done? I am assuming that well it is subjected to some axial force P, right. Now, this you see I am considering a simple stub over here of length d. This fellow is now when it is deforming, this is dx and this one is nothing but what? dw dx into dx, this fellow. So, this chord length of this chord what? Length of this chord is nothing but dx square plus dw dx square into dx square. So, dx root, you understand what I am doing, right. So, I have the beam column and then we are deforming, right. So, deflection is W. So, this is being this chord. What is the length of this chord? The length of this chord is nothing but this square. I am approximating this chord by line, right, assuming dx to be infinitely small. So, this is root dx square and then this distance is nothing but what is del W del x multiplied by dx, right. I am taking square root of that. So, this what I 1 plus dw dx square and then I am, if I write it, it is 1 plus half dw dx square, right. So, ds minus dx by dx is equal to what? Is nothing but half dw dx square, which is nothing but strain, right, strain. So, out of plane deflection is causing axial strain, out of plane deflection is causing axial strain and this strain is nothing but what? Which strain is this? This is nothing but von Karman nonlinear strain, because if you can recall from your radiation notation epsilon ij half u I comma j plus u j comma I plus u k comma I u k comma j. So, this is will not be there, okay. But then this square, this is one, of course there. So, when I am simplifying epsilon xx is what? It is nothing but du dx plus half du dx square plus dw dv dx square plus dw dx square, right. Now, for a beam, the in plane direction u is very small. So, its gradient smaller, there is no w, so there is no v, and then only this is the important, this term will be there. So, this strain is called von Karman nonlinear strain and this is valid for moderate rotation, okay. Many people call it large deformation strain. No, this is wrong, not large deformation, moderate deformation, okay. So, this is nothing, this is another simplified derived von Karman nonlinear strain. Now, so this strain, so how this, so if under this loading, this fellow, whatever under this loading, this fellow is what? This fellow will come and this fellow is deforming. So, there is some deflection, this deflection is nothing but what? Integration axial force epsilon xx into dx, integration 0 to L, and this epsilon is nothing but half dw dx square dx. This is delta. So, p into delta. So, minus p into delta, p into delta, That means the strain energy integration for beam column is nothing but d2w dx2 square minus p by 2 integration 0 to L dw dx square into dx. Do you see that? How it is coming, right? For the beam column, the strain energy, other than bending, there will be always a component which is by the work done by the axial force, and that deformation by the axial deformation is obtained by integrating the von Karman nonlinear strain. Von Karman nonlinear strain, so it is basically axial strain due to out of plane deformation. We know if there is extension of this bar, then if strain is what? Strain is nothing but change in length by initial length, but here change in length is along x direction you have to consider, but deflection is along w. So, in order to capture that, you have to consider higher order terms, non-linear. That is why strain become non-linear. You understand, right? Because del u del x, there is no u, no in plane deformation. There is no in plane deformation, but still there is in plane strain. And why it is happening? Because in plane strain is occurring due to out of plane deformation, and that is described by von Karman nonlinearity. Clear? So, this is the functional expression for the strain energy. So, now we will play with this. So, in the next class we will do this, we will derive the governing equation for the beam column. Okay? Thank you very much.